Every time I do one of these things lately, I've been leaving you with a few questions that we still need to answer. What about lone pairs? What about this? What about that? How does it happen? We're getting our way through answering most of those questions. And this piece is going to be answering another one of those questions. What do you do with lone pairs? And that was a question I left you with. What we know is that lone pair has a lot of repulsion. It's going to repel things as far away from each other as possible. So we also know that lone pairs are going to use hybrid orbitals. So that part is taken care of. What we want to focus on is what happens to the shape. What do we do with the shape? What becomes those new VSEPR shapes? So if all the electron pairs are going to be repelling each other as far away from each other as possible, and they all need a place, and they're all going to be going into hybrid orbitals, and we still have to figure out multiple bonds, then what do we do for VSEPR shape? We also have to remember that the lone pairs are going to repel other lone pairs, and they're going to repel bonding pairs. They're going to be repelling more effectively or more strongly than bonding pairs. So that's going to play into this as well. We had this table one other time. I'm not going to be filling in this table now. I think it's a really good organizational tool, so you might at some point want to go back to that table last time and fill it in. I would actually recommend redoing it so that you can do all of the similar ones together, right? The total number of hybrid orbitals, keep them all together. Because the way we filled it out last time was all of the 2 and 0, 3 and 0, 4 and 0, and so on. And now we're going to have the lone pairs in there as well. Okay, notation that we're going to use. I'm still not a big fan of this kind of class notation, but AX2E, some people do find it useful. I suppose it has its place, where E represents the lone pair of electrons on our A, which is our central atom, and our X's, which are our bonding pairs. What we're going to be doing is we're going to be throwing in some E's today, okay, the lone pairs, the non-bonding pairs. On the diagrams that I'm going to show you here, I'm going to represent these lone pairs like this. I'm going to kind of ghost this picture on top of something. If this is where that thing is going to go, what would it look like then? And it's important, I think, to understand that if you were able to see a molecule in space, if you were able to see a molecule, you would see the central atom and the atoms that are bonded to it. You would not be able to see the electrons. So if you were to look at a central atom, or you look at a molecule that has a central atom with lone pairs, the lone pairs are not going to be visible, but they are going to influence the shape. And that's kind of the approach I'm going to be taking here. So I'm going to start with this one because this is the first one that has a meaningful thing to do if you have a lone pair of electrons. I start out with bonding angles of 120 degrees. And again, like before, I'm not going to be asking you to tell me what the bond angles are. I might, though, give you a question of what about this situation, which is a little bit different. How would the bond angles compare? Would they be bigger or smaller? And that answer comes down to, well, lone pairs repel more strongly. If I were to replace one of those, and they're symmetric, so it wouldn't matter which one, if I were to replace one of those with a lone pair of electrons, and I didn't fix my note, there we go, I did fix my notation, then my notation changes, not that that matters, but my molecule stays, it's different now, right? I'm not going to be able to see that lone pair of electron, but it is going to have an influence on the shape. It's going to actually, because it's repelling more, those bond angles are going to be less than 120 degrees. I'm going to call that thing bent. Our names aren't going to be particularly inventive. I've got something that looks like maybe it could have been straight, but it got bent into a not linear arrangement. AX4, our tetrahedral. There's a couple of options here for putting lone pairs on it. I could put a lone pair in this location, and again, I rolled through the bond angle quite quickly because I don't really need it. That location, in that case, what I would have is one lone pair. I wouldn't see it, but it would turn that thing into something that looks more like a pyramid. Pyramidal is or pyramidal if you prefer. Bond angles are going to be a little bit less than 109, but again, I don't want to spend too much time talking about bond angles. Common example of a molecule that does that is this: 3 bonding pairs, 1 lone pair. If I go back to that original tetrahedral, let me go back to that original tetrahedral, and I look at what it is if I have 2 lone pairs. Again, has an influence without being visible, that is going to be called bent. Is it the same bent as the previous one? It doesn't really matter. We're not going to say it's this kind of bent versus that kind of bent. It's bent. Okay, 3 atoms that I see, and the angle between them is not 180. It looks like it's a bent thing. Again, bond angles that I'm not too worried about, yet I keep including them. Water molecule, and I think we saw that on the previous time. Central atom with 2 lone pairs and 2 bonding pairs. This is one, this trigonal bipyramidal, this is one where, because I don't have the symmetry that the other ones did, the first lone pair in is going to matter. There's effectively a choice. I don't really want to make it sound like it's a choice, as if you can just toss a coin and pick. But if I were to look at that thing a little bit more carefully, what I find out is that if I put a lone pair in that position, that lone pair is 90 degrees to 3 other groups. If I were to put that lone pair instead into this going around the middle orientation, that bonding pair, or sorry, that lone pair is 90 degrees to 2 other groups. And those, yeah, it's 120 degrees to a couple of other groups, but 120 is far enough away that it's not really a big deal. So what it ends up happening is the best location for that is in going around this middle part where I've got 90 degrees to 2 other groups. So that becomes a shape. Now, I didn't rotate this, maybe I should have, but if I were to look at this thing sideways, if I were to take that molecule and tip it over, it would end up looking like a seesaw. There are other names for it, but I think the best name is seesaw because it's at least descriptive. That's a molecule that has that, so sulfur tetrafluoride, but we're just going to keep moving on from there. If I take that one and I want a second lone pair of electrons, it's actually going to go into the same place, into that going around the middle, so that I end up with lone pairs that are 90 degrees to 2 groups rather than 2 lone pairs that are 90 degrees to 3. That, if I were to look at that and rotate that molecule, then it's going to be T-shaped. Okay? And again, an example, but we don't really care about the examples. You're going to have to draw the Lewis diagrams anyway. If I had a third lone pair of electrons, same place, going around the middle, so that each one is only 90 degrees to 2 other bonding groups, so those lone pairs as far away from each other as possible. And you might be thinking, yeah, but no. Then I end up with that. It's going to be a linear molecule. I didn't draw out what it is, and it doesn't really matter. Couldn't really think of a good example that happens in real. But again, you're going to have to draw the Lewis diagrams anyway. You might come across it. Starting from this one, we're back to symmetry as a starting point, so it doesn't really matter which one we put it into. I picked the bottom one because it was convenient for me. It also had a diagram of the structure once it's finished. So that now, if you were to make a geometric shape out of that, I've got a nice flat square base and then all going up into this one corner. So that is a square-based pyramid. Pretty obvious, hopefully. If I go to a second lone pair on that, I want those lone pairs as far away from each other as possible. And again, it doesn't really matter where I start because I will have one that is directly opposite to it. That will put my lone pairs as far away from each other as possible, and my alignment's a little bit off there, but I end up with what's called a square planar. All of those are in the same plane. You could lay that molecule flat on a surface and it wouldn't dip around too much. Okay. You could have others. Those are pretty much the ones where you're going to be working with. If it went on something else, you could probably figure out what it is. Okay, so where we're at right now is we can do VSEPR shapes for everything. We can do hybridization for everything. But you also, coming out of this one, you want to be able to explain why a certain orientation. So for example, that trigonal bipyramidal one as our starting point, why does it go into around the middle instead of on one of the up and down, one of the ends? Anyway, but that'll be a question for another time. Talk to you later.